Assalamu alaikum, my name is Masters. You are watching my YouTube channel. In this video, we are going to simulate a system in which we are going to simulate first a gas turbine, and then coupled with the gas turbine, there will be a heat recovery steam generation system, and the steam that will be produced from the HRSG, we will simulate and we will run a steam turbine from that steam that will be produced from HRSG. So why, along with gas turbines, you are always having a HRSG because at the exhaust of a gas turbine is having a large amount of heat. So you can use this large amount of heat to produce steam, and this steam can be used to run a steam turbine that you can see. We will simulate a steam turbine, or you can use this steam as a utility at your industrial plant or at any industrial process. So our simulation will be consisting of three parts. First of all, we will simulate a gas turbine, and then we will simulate a HRSG system, and then in the last we will simulate a steam turbine. For the simulation of a steam turbine, after steam turbine, we will apply a condenser and condense all the steam and recycle this water into the HRSG system again. So we will see that how we can going to simulate as we move along the video. Before moving to the simulation, I can show you a small schematic diagram that we will be going to follow for the simulation. So if we go to the gas turbine, so it is, so now you can see that our gas turbine mainly consists of three parts. First part is the compressor, in which air is compressed. The second part is the combustor, in which the compressed air and fuel is burned to produce a large amount of heat and large volume of gases. This large volume of gases carrying a large amount of heat is used to move these three-stage turbine blades, and then this after transferring their energy and rotating these blades of the gas turbine, and these gases went into the environment. This is simply a gas turbine. So after this gas turbine, at the here at the exhaust, we place a HRSG system, and you can see this is the open cycle for a gas turbine. So we are following this open cycle. But if we place a heat exchanger over here at the exhaust, like you can see over here, but this is the closed cycle diagram. We are not following over here this closed cycle diagram, but for just to represent that how a heat exchanger is present. So I had placed this diagram over here. So we have placed a heat exchanger over here, and after these gases went into the environment. For a closed cycle, and these gases that is being venting into the environment, you have to recycle it back into the compressor. So we are simulating open cycle gas turbine, and this is the ideal case, and we are not following it. So before moving to our simulation, we will go through a simple flow diagram that will be representing that well what we are simulating. So first of all, we will having a air that will be compressed in a burner. We will use a stoichiometric reactor in our Aspen Plus, and a gas turbine, and then the turbine. And this exhaust of gases that is having a large amount of heat will pass through three heat exchangers that are forming our HRS: a superheater, evaporator or boiler, and an economizer. After exchanging heat from the economizer, the gases will went into the environment. Also see that where and how we will use a steam drum. Steam drum is normally present after the economizer, and the recirculation of evaporator happens here, and the liquid phase and vapor phase separates, and this vapor phase, as it is saturated, it goes to the superheater for being superheated. So it is the gas turbine. After the gas turbine, sorry, it is a steam turbine where we have used our heat, and then we have used the condenser, and then we will recycle our this water back to the economizer. So we will see that how we are going to simulate it. We come to our case study here. In the case study, we have given the fuel flow rate, and the fuel temperature and pressure is given to us. The air is available at 101.3. The fuel consists of only methane gas. So now one thing is missing, that is the air flow rate. So you have to find this air flow rate from stoichiometric calculations, that for this 10 kg mole per hour of methane gas, how much amount of air you require. So you can, it is easy, you can stoichiometry calculate. I had stoichiometry calculated. It is 100 kg mole of R, kg mole per R. Air is kg mole, sorry, it is K mole per R is required. So for if you don't know how to stoichiometry calculate, I have a playlist in which on my YouTube channel where you can find or where you can run the stoichiometry calculations. So we have to use the excess here. We will use our excess here, and we have to find the power our gas turbine will be generating that can be used to produce the electricity by using a steam generator at the downstream of our gas turbine. So let's move to our simulation. First of all, I will add my components. So my components will be methane, then carbon dioxide, then water, then oxygen and nitrogen. So I had added my components. After this, I will press this next button. In the next button, I have to add my property package. So in the property package, I can use Aspen Robinson. After that, I will press this next. Just press this run button. After that, I will go to my simulation. So now here you can see, first of all, I need a compressor, a burner, and a turbine. So for a compressor, I will go to pressure changers, and here it is a compressor. And from here, this is the sign of a turbine. And in the reactors, you will use R stoichiometry for a simulation of a burner over here. After this, after this, just press this material stream. So now I am adding my material streams. Now I can name my streams. First, this is the air. So now you can write the compressed air, and here you can write as gas, and here you can write as exhaust gas. So now it is okay, and after that you have to end another stream that is required, and that is of fuel. So I will press this stream. Here you can write as fuel, double click on it, and just give it over here. So this is your fuel. So now this is all for a gas turbine. So I can press this air, double click on this air. So now what was the temperature of air? You can take the ambient temperature of air. Pressure 101.3 to 5 kilopascal was given. So you can write 101, or you just write 1 bar, that is equal to 101.3 to 5. It is not same, but it is very near to that. So what was the total flow rate for air? It was, I said that you have to calculate it, and I had calculated that is 100 kg mole per hour. So here you can write as mole fraction, and uh, in the mole fraction, oxygen amount is 0.21 and nitrogen is 0.79. Press this next button. So here now it is the fuel stream. So our fuel stream temperature is 70 C and its pressure is 20 bar. So its temperature is 70 degree and its pressure is 20 bar. So the molar flow rate of our fuel gas is 10 kg mole per hour, and it is consisting all of methane. So molar flow, and you can write here as 10. So now again you can see blue tick has appeared. So this stream minimum requirement has been completed. So after this, press this next button. So now it is our compressor, B1 compressor. So if I go to main flow sheet, so it is our B1 compressor. So now here, select a compressor type. You can use, I am using here isentropic using ASME method. So now you have to specify any one of these things for the simulation to happen. So as I go to simulation, so it says that the air must be compressed and sent to a combustion chamber with a pressure ratio of 8. So pressure ratio we have been given, so pressure ratio of 8. So pressure ratio of 8, and you have to now specify, if you want to specify these efficiencies, but we have not given, so just leave them as such. So now after this, press this next button. So now here, what is our B2? B2 is our this turbine. So again, I will press here as on the isentropic and select here as turbine. After that, now here I have discharge pressure. So now coming to the discharge pressure of a gas turbine. So if I go to this diagram, so you can see we have to specify such a pressure or decrease the pressure or give a pressure up till now that it is capable of passing through all these heat exchangers, and then at this point it is above the atmospheric pressure so that it can be easily vent into the environment. So we have to calculate the delta P over here, delta P over here, delta P over here, and then we have to specify the pressure over here. So you have to plus all these delta P's, and if and the place a value over here that is above the value over here, and this value must be above the atmospheric pressure, because if you will specify here, you will calculate that here pressure will be 1 bar. So after passing these three heat exchangers, there will be a pressure drop, and this after say that its pressure here becomes 0.9 bar. So now it is less than the atmospheric pressure. So now it will not, these gases will not went into the environment, and you will be having a back pressure in your system. So now here I am considering the ideal case and saying that no pressure drop happens over here and here, and I am specifying my exhaust discharge pressure as 1.2 bar. So that's all. So now I will press this next button. After this, I am into my reactor. So as it is an adiabatic reactor, adiabatic reaction, so give a duty 0. And for pressure, you can because our air pressure was compressive, so now for pressure our reaction is happening at the combustion is happening at 8 bar. Select this vapor only because reaction is happening in only vapor phase. So now after this, press this next button, and in the next, now you have to specify the reactions. So just create new, and here methane is burning with oxygen to produce our carbon dioxide and water. What are the methane coefficients? Here methane coefficient is -1. It is reacting with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. So now I think this is the balanced equation for our reaction. So after this fractional conversion, just I want the 100% methane to be converted. So I will write as 1 of our methane. So now you can see you can see that run button has been activated. So you can say that I can run this simulation. So I will press this run, and you can see that my results are available. So now what we have to find? We have to find that excess air is present in combustion, or the power that is required. So again, for power, just press here, and this is our B2, and go to this results. And here, this is the amount of power that this turbine is generating. For our excess air, press our B3 block, go to this stream results, and in the stream results, press this molar flows. After going into the mole flows in oxygen, you can see that 1 mole of oxygen is going unreacted. So our oxygen is excess form. So one thing you have to keep in mind, then whenever there is a combustion reaction, you have to keep this oxygen into excess form. in your vent, because it shows that your methane is completely burned. And if your methane is going unburned, so it is a fuel gas, and then it is not feasible for you to waste your fuel gas, because you are spending some money on your fuel gas. Now we move to the second part of our simulation. So now we are going to simulate our HRSG system. Here one thing is that the steam that you want to produce will be specified by you. So now here I want to produce a steam at 40 bar pressure or 4000 kilopascal pressure. So this 40,000, how we will achieve this 40 bar or 4000 kilopascal pressure? So it will be defined, or it will be maintained by our boiler feed water pressure. So you have to maintain the boiler feed water pressure, pump pressures a little bit higher, or you can find all the pressure drops that will happen in the heat exchanger or in the steam drum, and then you will define your boiler feed water pump pressure, and this boiler feed water pump pressure will define what pressure of steam you are going to produce. After this, one thing is that how we will find the mass of water that can be converted into steam from the amount of heat or that is produced from this gas turbine. So for this is the formula. Here you can see that this is the formula, this is the amount of heat, this is the mass of water we want to find, and this is the heats. Because if I go to the vapor liquid equilibrium DOM or diagram of water, so now you can see that this 2 to this 2 hash 2 bar is representing the sensible heat, and this sensible heat is representing into the formula by this delta H water, or HF minus HA. You can also write CP delta T over here also. You can use the formula MCP delta T, or here you will write only CP delta T over here. For after this, now you can see that here, if I am if my so now here, if temperature pressure is 1 bar, so here it is the boiling point of water, it is 100 degrees C. If I continue to add add heat in it, so this is the latent heat. So now water will continue to evaporate, but its temperature will not rise. So now, after adding all the amount of latent heat that is represented by HFG, and then this point will come here. Now temperature is now 100 degree, but all of the water is being evaporated into steam, because we have to produce superheated steam. So now if you continue to add heat, so this heat is represented by this HF minus HG. So up to this up to any point, or up to any temperature. So now if you define the temperature, so I have defined the temperature because that I want to produce a steam at 350 degrees C. So now all these values you will find from the steam table. Just go to the steam table, go to the saturated steam table, and find HFT value by going into the 40 bar column or 40 bar row of steam table, and from there also find this HG value. And for H superheated value, you have to, because now you are dealing in single phase, so you have to now need two things. One will be this 40 bar pressure, and then you will also define this temperature. When you will define the temperature and pressure, you will find this H superheated value. Just put the values over here. This Q will be obtained from this exhaust, the turbine exhaust temperature. You will find this amount of heat, and just divide it, and you will find the mass of water. So now I had calculated, and my initial guess for this is 1800 kgs per hour is the amount of water that can be converted into steam of 40 bar at 350 degrees with this amount of heat that is being produced with this gas turbine exhaust gas. So now uh, I will go to my simulation. Now I will add my heat exchangers. So I will go to the exchangers. Here, this is my superheater. Again, this will be my boiler, and this will be my economizer. So now you can, I will double click on it. You can write the superheater heat superheatex. Here you can write as evaporator or a boiler evaporator. Here you can rename as economizer. So these exhaust gases will be our hot stream, and the water that it will be entering is our cold stream. So now I will make my connections. First of all, I will go to my this stream. So here it says this hot required, and here it says that cold required. So that is my cold stream, that is my water inlet. So here I can go it and rotate it. So again I can rotate it over here, and now I can take my this 6 to over here. I will press this and again I will rotate it. So now it is okay. Again, I will go to my material stream, and now I will specify my cold outlet, and this is my hot required, and this is my cold. So you have to be very specific in specifying these connections, cold, and so here again I will press this, and this is my hot required. So for hot required, I will press this exhaust gases, and this is my cold required, and this is my hot gas. So I will press this, and this is my cold required. So you have to keep this thing in mind, that water is our cold stream, and this exhaust gases is our hot stream. So water in, here it is water out, and at the exhaust end of this evaporator you will be having steam, so you can write as steam. So now I'm going to complete my connections. Go to this material stream. So it is hot required, so it is our vent gas. So just press this and make its connection with this hot required. So it is gone something wrong. Double click on it and press connect it with this one. So for 11 you can write as exhaust gas 1. And after that, this gases from passing heat through this, it will again pass through the economizer. So it is hot required. So yes, it is hot required, and then this hot will be venting into the environment. So it is our vent, and this 12 will be our exhaust gas 2. So that's okay. So now there are four connections. There are four connections. So here I have to just specify another stream for my superheated steam. So it is my superheated steam. Just press this and rotate it. So now this will be my superheated steam. Super steam. Superheated steam. So that's okay. So now I will specify one by one. I will specify all my heat exchangers. So first of all, you have to specify the water inlet conditions. So double click on it. The temperature I am going to specify as 102. Pressure I have already told you that it will be 40 bar. And for water, we have find that 1800 kgs per hour water will be used. Again, go to this mass flow. Here you can write as water, and it is 1800 kgs per hour. So now you can see that it is good to go. After this, and you can press this next button, but for understanding, I am going to separately specify all my heat exchangers. So here in the heat exchanger specification, go to the specification, and so now here if I go through my main flow sheet, sorry, main flow sheet. If I go to my main flow sheet, so it is water, as I already told you, is our cold stream, and in the economizer, I want I want that all the sensible heat is from 2 to this 2 bar is added. So for the sensible heat to be added, I will press this heat exchanger, and here I will specify the cold stream outlet vapor fraction. and here I will specify my value as 0. So now this 0 will show that how much amount of heat you need for taking this water at this pressure to its boiling point or just below the boiling point. So you can see my specification has been okay, all are good. So I will go to again my main flow sheet. Here I will specify the evaporator, and here again I will specify my hot stream outlet vapor friction, and now I will specify that it is this point because now I want to add in this evaporator I want to add my latent heat, and at this point now all my water is present into vapor phase. So it will, so now here I will write as 1. So all the input has been performed. So now I will go to my superheater. In the superheater again, now if you see, go to the case study, if you go to the case study here, we have to produce the superheated steam at 350 degree. So now here I will specify the cold steam outlet temperature and rename as 350 degrees. So it is all good to go. So now you can see that run button has been activated. So I will press this run, and you can see my all the simulation has been solved. So now here I can uh, just close them all and go to my main flow sheet, and here you can see this vent gases is venting into the environment. So now I can this economizer super. So there is, this is the economizer, and here I can go to my stream results, and here you can see the temperature of our vent gases, that is 448. So it is a large amount of heat is still wasting into the being wasted into the environment. So I can increase this amount of water and see that it perform calculation and there will be no temperature cross. So just reset it and press this run button. So now you can see my results are again available. Go to this now. So now you can see that this temperature of exhaust gases is reduced. So you can still you can increase your flow of water, and this temperature you can minimize this. That's all. I am not going to more simplify it because the video will go a bit longer. Again go to this flow sheet, or you can also use a design spec over here to specify or your to economize your water flow rate with this economizer outlet temperature. So now if I go to my main flow sheet, so we have all now simulated our heat recovery steam generator. So now we will in the last we will be simulating our steam turbine and a condenser. So again, go to this pressure changes, and here place the steam turbine. So now I will double click on it, and again a material stream, and let me rotate it. So now, so double click on it, and here you will specify it is a turbine. Go to this isentropic, and again you have to specify the discharge pressure. So it is a condensing turbine, so you can write as 1.1 bar as your discharge pressure. So you can see that all the minimum inputs are completed. You press this run button. So now it says that you are having some error, so you can go to this b block and see that, so it says the liquid phase is present. So now as we are simulating a gas condensing turbine, so there is some liquid phase present. So for this error, just go to this convergence, and here you will specify your vapor liquid for this simulation to happen. Just press this reset and press this run button. So now you can see that my results are available. Again, go to this result summary. Go to the summary. Sorry, go to the results. So that is the amount of heat that is being produced, or you can say power, and you can use this power or steam as per your requirement. So now in the last thing, what was our task is to condense this stream and reuse as a reuse in this economizer as a water inlet, and then there will be a closed loop. So again, I will go to my exchangers. It is a heat exchanger. So I will place. So sorry, I will not use a heat exchanger over here. I can use a heater over here. In the heater, I will now double click on this, and this will be my inlet. Again, specify a material stream. That is my outlet. Double click on it, and here I have to specify two things. For pressure drop, I will take as zero pressure drop, and in the place of temperature, I will again go to my vapor fraction and say that no amount of vapor is present, and I will specify that no vapor is present, all of the water is present. For this, I will press over as zero. So now you can see that run button is actuated. So I will press this run button. So now all my simulation, so my this block is also completed. So go to this result. So this is the amount of heat you have to provide it. You can use cooling water, or you can use a heat exchanger, and you can use a cooling water to reject this amount of heat over here. After this, go to this main flow sheet, and now I have to recycle it over here. Before recycling it, one thing I had forgotten, I had not simulated the steam drum over here. So let me simulate a steam drum over here. So now drum is present on this water out. This water out is not going to this evaporator. And generally, at our industries, this water from the economizer generally goes to the steam drum. So I will press this and I will break connection. So now connection is break. So I will delete this one, and this will be my boiler. You can write a steam drum in. So it is steam drum in. So I will go to the separator. Just place my separator over here. Double click on it, and this will be my inlet. So my steam drum is having two streams. It's vapor. The vapors that will be that is produced from the steam drum is going to our superheater. So again, I will go this, and here this will be my superheater inlet, and this my liquid inlet will be going to my evaporator. So you can write as evap evaporator in. So now I will I will double click on it, and this will be my cold required, and I will reconnect it over here. So after that this evaporator out is again going into our steam drum. So I will I will break this connection as well. So I will delete it, and I will rename it re evaporator. So I will double click on it, and this will be my inlet. Okay. So now after this, for achieving vapor liquid equilibrium in the steam drum, this 17 stream is going to our superheater. So I can write as to superheater. So here I can double click on it, and here I will press this. So now here you can see that what's next. You can go to this next. What thing I have been remaining with? It is my flash drum. So now here again go to this duty. just press this 0 because no heat balance will want, because all there will be natural vapor liquid equilibrium separation will be happening over here. For pressure, you can write as 40 bar pressure. So now you can see run button has been actuated. You have pressed this run button and you can see all my results are available. So now in this way, if I again go to my this results, vent stream results, and here see that if there are some changes that are present or not. So again go to the stream results, and here you will see that is not a much variation in temperature. Actually, before the steam drum, it was 376, but now it is 374 degrees. So again, just close this all windows, and now I have to recycle. So you can write as recycle water. So now the last step is to recycle the stream back into this economizer. But if I double click on it, so the stream pressure is 1.1 bar, but here for the water inlet, the pressure was 40 bar, and this 40 bar was the boiler feed water that is being used to produce the steam. So now I have what I have to do. I have to specify or place a pump over here. So I will go to my pressure changes. Here I will select a pump and go to my material stream, or just double click on it. So now I will double click on it and place it over here, and I will double click this water inlet and connect connect this stream with this one. So after that, I will go to my double click on my pump to specify my pump. So it is a pump. I have to specify my discharge pressure. So I will write as 40 bar. So now the minimum requirements have been fulfilled and the run button is actuated. So I will press this run button and you can see my results are available. So in this way, after installing a pump, we had recycled our we have made a closed loop for the steam and water. Here, all the this condenser will condense all the water. You can also use a heat exchanger and cooling water for condensing this steam, and that is steam water mixture coming from this steam turbine. So this is my main flow sheet, and I hope you like the video. Inshallah, meet you in another video.